nanohub.org.
Online simulation, and more for nanotechnology.
Hello, everyone. Welcome to the latest, NanoHub machine learning workshop series. Welcome to our latest workshop. So I would like to welcome you all on behalf of Professor Strachan and the entire NanoHub team. So our speaker today is Dr. Anjana Talapatra from Los Alamos National Laboratory. Anjana is a director's postdoctoral fellow in the Material Science in Radiation and Dynamics Extremes group at Los Alamos National Laboratory. Her research involves combining high-throughput density functional theory and machine learning methods to accelerate the search for new materials. She previously worked at Texas A&M as a research scientist. She got her PhD from Texas A&M in the mechanical engineering department in 2015. Anjana has worked on a wide variety of materials-related problems using CalFAT techniques, DFT, and machine learning. Her PhD was focused on thermodynamics of phase transitions in shape memory alloys. So today she will be, giving a presentation and walking us through on a machine learning-aided hierarchical screening strategy for materials discovery. So Anjana, please go ahead. You can get started.
Okay, thank you so much, Arun. So today I will be going through some slides and a tutorial, and I will give an overview of our machine learning-based approach to the discovery of new wide bandgap double oxide perovskites. So throughout this talk, I will try and include a lot of suggestions as to how to go about using material science, using machine learning in material science problems. However, please note that these are based on my personal experience and by no means are expert ideas. So moving on. Okay, so in our work, we are specifically interested in perovskites with wide band gaps. So now perovskites have been around for almost 200 years, and they still continue to attract a lot of attention due to their fascinating and wide-ranging properties, which actually find use in a lot of diverse applications. So the typical perovskite represents any compound with a ABX3 type osteoisometry with the crystal structure shown here. And in each of these A, B, and X sites, we can potentially include more elements, leading to double and higher order perovskites. So while there are a large number of known oxide perovskites, a vast chemical space remains unexplored. And there are millions of potential oxide perovskite combinations out there, if only you know how to search for them. So of course it isn't easy. Otherwise people would have already been, explored the whole periodic table. So all these millions of compounds, we first need to screen them to figure out which compositions are actually thermodynamically stable and which can be synthesized experimentally. Which of them will actually have a band gap or be an insulator, and will they have a band gap that is sufficiently large for our purposes, right? So before I delve into our strategy to screen these millions of possible compounds, I would like to concretely define the problem we are trying to solve. So our objective is to down select from millions of potential compounds to a relatively small and tractable set of promising wide band gap oxide perovskites. Why oxide perovskites? So the perovskite structure can accommodate up to 90% of the metallic ions in the periodic table, giving us a wide range of materials to work with. So this structural complexity, it also affords us the ability to tune the band gaps of these materials to what is required for a specific application. Additionally, perovskites exhibit many fascinating properties, opening up the gate to functional optoelectronic materials. Parts of what I will discuss today has already been published in Chemistry of Materials as shown here. And so if you do want to know more, feel free to look it up. So to define the structural space of materials that we consider, we look at single and double oxide perovskites. We allow for mixing of up to 2 elements in both sides, in the A and B lattices. And to keep the problem tractable, we only look at 50-50 mixing. The idea being that if we do find some promising 50-50 compositions, we can always take a closer look at the full range of compositions for a particular chemical system. We also focus on cubic perovskites, even though perovskites are known to stabilize in other symmetries. We account for this separately. Okay, so as I shall discuss later. Thus, for all the chemistries, we constrain the structure to cubic and consider the more commonly observed rock salt ordering. So we consider rock salt ordering for the A and B lattices and to keep the high throughput calculations tractable. So for our domain, we considered 68 elements of the periodic table to build our search space of oxide perovskites. Since we consider mixing of up to 2 atoms in the A and B sites, it gives us around 5.2 million combinations. So our task is now to come up with a strategy to screen these 5.2 million compounds and select from among them a small set of promising materials that we can work with. And I think I already went through this. So we look at single oxide perovskites and then double oxide perovskites. And these are the assumptions that we make: 50-50 compositions, 2 elements per ion site, cubic structures, and rock salt ordering. So the question here is that, do we really need to use machine learning, or are we just using it because, it's a cool thing to do today? So we are looking at data sets of millions of compounds, and there is really no other way than ML to tackle such large data sets. Secondly, we don't have a good idea of the physics that relate the composition, stability, experimental synthesizability, and the bandgap itself. And hopefully we can use machine learning to shed some light on these complex relationships. Also in our problem, there are some things that we do know how to calculate, albeit approximately. But even though we know how to calculate them, we can't really do it for millions of compounds. And again, there are some things that we do not know how to calculate. I mean, how are we supposed to know that even if I'm able to predict something to be thermodynamic stable, that does not mean that somebody is going to actually be able to synthesize it in the laboratory. So we have a combination of things that we know how to do and we don't know how to do. We have another combination of very large data set, and putting all these together, really machine learning is the best solution. So moving on, so after we identified these 5.2 million candidates, our first step was to check for chemical compatibility. That is, select those compositions that lead to charge neutral compounds and have the correct atomic radii to form perovskites. This step allowed us to discard about 80% of the possibilities, leaving us with just about under 1 million compounds, right? So we just have around 900,000 chemically compatible compounds. So in a hierarchical strategy that we are using, our next step is to select compounds that are likely to be thermodynamically stable and experimentally formable or synthesizable. Once we have those, we select those materials that are likely to be insulators, and we discard the metallic compounds. Finally, we predict the band gaps of these predicted insulators and select the ones that have a wide band gap. For these 4 steps, we build machine learning models. And ideally, at the end, we will find a small set of promising materials, which we can then analyze in depth. So to implement a hierarchical strategy, we start with our data set of these chemically compatible compounds. From among these, we filter out those compositions that are not experimentally formable. Simultaneously, we filter out those compounds that are not thermodynamically stable. After this, we take the intersection of these compounds to find out those which are stable and formable. And on these, we apply another filter, which is basically a classification model to filter out those materials that have a 0 or very low band gap. We choose a 0.5 electron volt threshold here and only keep those candidates that are predicted to have a wide band gap greater than 0.5 electron volts. Once we have these wide band gap candidates, we use a regression model to predict the low fidelity band gaps of these materials. Depending on the application we are interested in, we select the materials that have suitable band gaps and then use another regression model to predict the high fidelity band gap. So, and ideally we'll end up having some compounds which you can either analyze further or else go in for experiments. However, before we implement our this discovery strategy, we actually need to build these models. And so next I will focus on how we actually build the models. In the interest of time, in the tutorial today, we will only cover steps 3 and 4. That is, we will cover 1 classification and 1 regression model and apply these models to discover new materials. Okay. So for a typical machine learning scheme, it consists of procuring the training data, coming up with a list of features that relate the data to the material to the target property, and then you use the data and the features to build your models, and finally analyze what you have to improve the models. You do some back and forth feature engineering to come up with the optimal features. If the model is good enough, then you append, is not good enough, then you append more data until you have a good model. Once your model is sufficiently accurate, you use it to predict on unseen data. So this would be a basic ML scheme for any problem you're trying to solve. So for our different models, we use training data from literature as well as by carrying out DFT calculations. To determine the features, we used element-based features and our domain knowledge, in addition to whatever insight we could gain from literature. So some things to keep in mind while building a training data set is that your model is only as good as your training data. So it is very important to cross-check over and over again and make sure that your data and everything that you have in there is completely correct. To increase the applicability of your model, it's also good to use features that are easy to populate. So for example, I do DFT calculations, and I obviously, because of that, I use in my training data, I technically have access to formation energy in my training data. But it is not a good idea to use formation energy as a feature in your model, because I intend to apply it to millions of compounds. That would also mean that for those millions of compounds, I need to have the formation energy. So that would not be tractable at all. And it would basically defeat the purpose of using machine learning. So important to use features that are easy to grab from wherever you're going to get them. Double check, triple check sources of your features and values of features. In my work, I have found that 90% of the troubles and wrong results and bugs that we have found can be attributed to mistakes in populating the training data. So for example, recently we discovered that we used a very reliable database for our data, and some values were off in there. So we basically had to go in and do all our models again. And ideally, you want to avoid that. Reproducibility and consistency. This is important in that when people publish machine learning models, the idea is obviously that you should be going in and be able to use those models. Other people should be able to use them to further their own work. And when I try to do that, I always, if I pick up a paper like that and find an interesting model, I always will go in and try to make sure that I can reproduce that model myself before actually using it in my work. So if I can't do that, I'm not really going to use it because I don't really have any confidence in what that model is all about. So it's important to make sure that everything that you're doing is reproducible, all data sources and everything annotated, and that you're using consistent data sources. So the next step is that for our actual ML machinery, we used random forest models for both classification and regression. We did try using other ML techniques, but in the end, random forests work best for our purpose, and we stuck to that. So it is important to choose your machine learning technique wisely. It's good to do baseline comparisons across different models and select one that is best suited to your particular problem and your expectations. Again, there's a lot of work in ML informatics that is already out there, and sometimes it is wise to make use of what is already available rather than to build your own. That said, it is important that you fundamentally understand the workings of whatever ML technique you are choosing to use before you actually use other black box software. So to make our models accurate and robust, we use cross-validation techniques to determine our model hyperparameters, and we did testing and feature engineering. So we did all this adaptively. That is, I ended up with a training data set of about 5,000 materials, but I started off small. I started off with about 1,000 materials and kept increasing them, trying to adaptively improve my model and keeping an eye on the performance metrics, making sure that I don't use too much data because that could lead to overfitting, and I don't use very less data as well. It is also important to analyze your data and results continuously to ensure that it makes sense intuitively. Ideally, as material scientists, you should be having some idea of the problem you're trying to solve. And so if something looks off, it probably is. So always better to go back and check. Avoid data leakage. This is really important. I see this happening quite often, that people use the same data to train and well as to test, and that is a definite no-no. That definitely compromises the accuracy of your model, and it's not really a good thing to do. So you should always take care that you're avoiding data leakage. So with all these suggestions, the next step was to actually build my training data. So to predict formability, which is the ability to experimentally synthesize a composition, we use an experimental training data set of single and double oxide perovskites from literature and databases such as ICSD. We found a total of about 1,500 compounds, out of which about 1,200 were definitely known to be perovskites, and the remaining were not perovskites. So obviously we restricted this literature to pure compounds and compounds with only a 50-50 mixing. Since these are experimental data, they're obviously not restricted to only cubic perovskites. For the thermodynamic stability and bandgap classification and regression, we use a dataset compiled using DFT. We calculated the ground state energies and electronic structures of about 5,000 materials using the PBGGA formalism, which gives us low fidelity estimation of the bandgap. Anyway, So for thermodynamic stability, we calculated the energy above the convex energy hull using the materials project database. And this is basically a metric that tells us if the specific composition is stable with respect to all the other structures within the chemical system and will not decompose. So a positive energy value of energy above hull indicates that the composition is unstable. So this energy above hull calculation is done for the cubic phase, which means that we are discounting lower symmetry phases, which might be stable when the cubic phase is not. Hence, we use a threshold criteria of about 50 milli-electron volts for assigning the stable and unstable labels to the compounds in this data set to account for these lower symmetry variants and crystal distortions and maybe potential metastable compounds. So with this criteria, we found that about 60% of the data set is thermodynamically stable, while about 40% is unstable. So looking at the bandgap values, we then assign anything that has a bandgap of less than 0.5 electron volt to be narrow bandgap material, while anything above 0.5 is a wide bandgap material. Again, with this criteria, about 1575 were found to have a wide bandgap, and these 1575 compounds form the training data set for our bandgap regression model. All right. So with the question of the training data settled, we started out with a very large set of ML descriptors, and we converged on a small set of features that were important to determine formability, stability, bandgap, range of the perovskites and their bandgap itself. So I have just listed the features that we finally used. So we started with a large data set and we narrowed it down to these. So for our training data set, both experimental and calculated, we ensured that the trained data spanned the whole domain so that we include effects of all chemistries. So these periodic tables here, they show a snapshot of the chemistries that are part of our training data set. So as you can see, they kind of span the whole periodic table, so that's good. So before I move on to our models and their performance, I would like to make a detour to discuss the relationship of formability and stability. So formability, as mentioned, we define it as the ability to experimentally synthesize a material. So it is a traditional method of looking at perovskites, and it relies on geometric criteria derived using ionic radii or bond distances, and it is a qualitative approach. Whereas stability is a thermodynamics preference to form a structure, and it is implemented using an energy hull construction to determine whether the structure is on the convex hull and will stabilize and not decompose. So it is not known with uncertainty whether a formable perovskite is necessarily thermodynamically stable or vice versa. The question we try to answer is that are both formability and stability necessary to guarantee the viability of a composition as a perovskite candidate, or is one a more robust metric compared to the other? So we found, and I will not go into the details here, but this study is part of our paper, so you can feel free to look it up. We found that stability with a 50 MeV threshold value for energy above hull is a stricter criteria for the viability of a composition. Also, other than trying to actually synthesize the material, there is no real way to validate a formability prediction. So our thermodynamic stability is a more accessible criterion for the viability of a composition as a perovskite. So our models were then trained, and here I have a snapshot of the model performance for the formability classification model. I have similar performance figures for all our models, so I will discuss representative results for a classification model only here. So on the left here, you see the ranked features, which tells us that the traditional structure factors, that is the tolerance factor and the octahedral factor, are a key feature in reducing the formability. A confusion matrix here, in which the green blocks indicate the materials that were correctly classified, shows that our model is actually very skillful at filtering out the non-formable compounds. The middle panel shows an ROC, or a receiver operating characteristic curve, which illustrates the performance of a binary classifier system as its discrimination threshold is varied. It is a plot of the true positive rate on the y-axis and false positive on the x-axis. So the 0, 1 point that is at the top of the screen here is where you would ideally like to see your curve. The greater the area under the curve, and here you see the great area under the curve is 0.96, which is good enough for us. The better is your model. So we see for our models, we use a threshold probability of 0.5, which is basically saying that anything which has a probability greater than 0.5 is a perovskite, or is formable perovskite. Okay, so similar to this curve, we have a precision recall curve on the right, and this is a plot of the precision rate on the y-axis and the recall rate on the x-axis. So a skillful model is represented by a curve that tends towards the coordinates 1, 1, that is the top right here. So anything close to here, you're in good shape, right? Again, here we see area under the curve of 0.99, which tells us that we have a very skillful model indeed. So this is what our formability classification model looks like, and we're happy with it. Then we move on to stability classification, and it's basically you can interpret the figures in the same way as the previous thing. You see that for stability, the tolerance factor moves down in importance, and some other features move up. Basically, HOMO and LUMO, which are the highest occupied molecular orbital energies and the lowest unoccupied molecular orbital energies for the B side. Another thing to note, it does seem here that it's mostly the B side features which are showing up as important. So just off the bat, it's possible to say that, maybe when you vary your B side atom, that makes a bigger difference than varying A sides. So again, we see threshold ROC curves and precision recall curves for the stability classification model, and things are looking great, nice area under the curves, and these points are pretty much right where they should be. So that's good. The next step then is the wide narrow bandgap classification, and this is where I will move on to using the tutorial. And you should basically have already received instructions to go to this link. And once you go here, you will see this launch tool icon, which you can click. And hopefully that should open up the tutorial. All right, so you should be seeing something like this when that starts. And meanwhile, I'll take a look at the questions. So let me see. Okay, what criteria is used to consider that the training data is complete or sufficient? Okay, so for our models, we had we basically went with we use the training curves to see when on the training curves you'll be able to see when your data performance metrics, you'll be able to see when your data saturates, when you have training curves. That is, your model does not improve any further when you add more data. So that is one way. Then for our regression models, we basically had a criteria of we need to be within 0.2 MeV, 0.2 EV of the predicted band gap. So it depends on your criteria is going to depend on what you are using, but for us it was basically ensuring that we are consistently getting the same similar results, and that our band gap is not beyond a 0.2 EV. Okay. Yes. So open source, yes, we use scikit-learn, and the things that are not available within scikit-learn we kind of built ourselves. So 50 MeV per atom criteria, like I mentioned that. Again, I think Anjana has answered that question, but yeah, you can take a look at the paper and even the ones that he has shown. But again, in our paper, we have a very detailed study of why we chose the 0.5 electron volt, 0.5 50 MeV criteria. So, okay, I think I'll move on.
You can continue with the tutorial now. Yeah, thanks. Okay.
All right. I hope everybody has been able to open up the tutorial. So to start with here, we have a computational workforce schematic, which basically it takes, this is a snapshot of whatever is going to happen in this tutorial. So there are two parts to it. So we have the model building first, and where we build the models, and then we use these models to predict on the candidate data sets. So we implement two models in this notebook. First is the classification model to separate materials that have a band gap greater than 0.5 electron volts from those that have a very low narrow band gap, and a regression model to predict the band gap of materials classified by our previous model as insulators. So now here it's important to note that we actually use this two-step process because it's important to do so. We just don't do it because we can do it. So if you give ask the regression model to predict something, it is going to predict a band gap value for you regardless of whether that material is an insulator or not. So for example, for what I'm trying to say here is that your regression model really has no way of knowing is your material an insulator or is it not. It just assumes that your material is an insulator and it will give you a band gap for that. So that is why we have this classification model in a step before it, so that we can filter out the ones which are not insulators and only keep those materials that have a band gap, so that our results are more, let's say, accurate. So if I had not had this classification model in the middle and I had just taken the stable and the formable materials and tried to predict the band gap for them, I would have basically got a lot of nonsense, right? Okay, so now moving on. So we are working with large data sets, and so I use the Python pickle module to manage our data sets. There are many things you can use. We personally use pickle, that just worked best for us. So first we load our data management packages. I use pandas to you do a lot of the work in there. So I import pickle, which is the data, how we load the data, and pandas again for data management. And then the last two things that I'm loading here are basically functions that I have written just to make everything seamless. Okay, so we run that, and that should load fairly quickly. Then we load our training compounds and the elemental data. So we load, so that's got loaded, and I'll just show you what these data sets look like. So the element data is basically all the data that is associated with the individual elements. So I just printed out what that data looks like. So it has all these values and all these properties in there. And I don't really use all of them, but I started off with all these properties, and then in the end, I filtered down to the properties that I already showed you. So our training compound, when we first load it, looks like this. It just has the A, because we are looking at double perovskites. I have them designated as A1, A2, B1, B2. So you basically have the elements themselves, the coordination numbers, the oxidation states, and whether it's an insulator according to our criteria of the 0.5 electron volts, what is the actual band gap that we have calculated, the functional group, what is the name of the compound, and whether it's stable, is it training data, and is it a single or double oxide perovskite, that is a data type. So then we populate the training data with all the features that we have finalized. And when we run that, we take a look at this training compounds, and now suddenly we just have a lot more features in there, all the features that we are going to use in our data, right? And so if you actually look at one data point itself, it will look something like this. So you have all the information for that data in there, right? And okay, so moving on, then we want to classify these oxide perovskites into narrow and wide bandgap materials. So we are going to first build our classification model. So here, I basically, I'm going to be showing you the end result, but ideally what you should be doing is that you keep running your model over and over again with more data and tweaking your parameters to ensure that you have the performance that you want. So here, we run our insulator classification, and first we see that, and I only have the test values presented here. So we see we have a very nice precision of 92%, recoil of 85, and a test accuracy of 94%, which looks very good, right? So then the test confusion matrix, I have it here. The train confusion matrix also you can see, and that looks pretty good as well. And then when you put it all that together, that's the entire data confusion matrix. So here we see the feature importances listed for this insulator classification. And we again see that the highest occupied molecular orbitals for the B site is important. But here you also see that the oxidation, the electronegativity, that is X, of the A site is also coming into prominence. So here you see that you can basically tell that which are the features that are kind of related to band gap, and what is the interplay of the two sites that you are using. So here again, but before you place too much confidence in these kind of feature importance plots, it's important to realize that there is a lot of noise that could be mixed in there. So in these cases, it's always good to use a random feature. Basically, just add in another feature, which you populate randomly with random numbers and use it as a feature. And ideally, that should appear very low in your feature importance list. If it appears at, say, number 10, then you can assume that everything above number 10 are real features with real importances, and anything below that does not really count towards your model. So that is a good way of looking at the feature importance plot. Next, once we have this, we will analyze the performance of our classification model, and by plotting the performance curves. So again, we plot the similar curves that we have seen there, and here we just report some values here. So we have precision, we have recall. Sometimes when you're interested in both precision and recall, it's good to take a look at the F1 score, because that is basically a metric which gives you the balance between the F1 and the between the precision and the recall. So again, we have good values for all of those. We plot our receiver operating characteristic, and we see that, okay, our area under the curve is good. And basically, and here again, here also we have a good area under the curve, and we see that this point is where we want it to be. So ideally, you should be going on reiterating in this step until you see the characteristics that you want to see, and the values are where you are happy with them being. Okay, so that is the end of our insulator classification model. And next, what we do is we look at the bandgap training. So for this, we are only going to use the data, for our training data set, we only take the ones which actually have a band gap greater than 0.5 electron volts. So now we first build that data. And then, so now we have the band gap training data, which we can look at if necessary. We plot it to see what does it look like. And we see, of course, all the data here is greater than 0.5 electron volt, firstly. Also, the data is spread pretty continuously over our entire domain of about between 0.5 to 4 electron volts, and that is important. It's important to make sure that your training data is spread out. Otherwise, you're going to have more accuracy in some areas and not so accurate predictions in some other areas. So then we use this training data to train our regression model. And again, we use a 80-20 split. That is, we train with 80% of the data and we test on 20% of the data. So we see what that looks like. And this is going to take slightly longer because it's a longer process. So we'll wait for that to happen. And while we are waiting, perhaps we can discuss a little more. So here, this is these scripts basically. Okay, maybe I can just move on. All right. So for the bandgap regression training, we see that our mean square error is 0.01, which is good for us. Again, mean absolute error is 0.08. The test regression values are slightly higher, but still, our criteria was basically to keep this up to around 0.2 EV, which is met here. And then the mean square error is 0.0, around 0.4 or 0.3. That's fine. Again, we have the feature importances here, and we see they're considerably different from insulator. So basically, it's interesting to note here that what is important for predicting whether something is an insulator or not is not necessarily important for predicting what is the band gap of that material. And this is an interesting thing that is definitely we're looking to analyze and look at more deeply in the future. So here I have the parity plots for my training data and my test data. And on the left, so you see that the training data, everything looks good. There are a lot of points which are on the predicted equals calculated line. Things are good. There is a little more spread for the test data, obviously. And here, this is where you should probably be looking at, probably go in and individually look at these outliers and see that what is the deal with them. So when we went and looked at these outliers, we found that these were the materials for which we had the least, which chemistries were least spanned in our training data. So so let's say this has whichever element it has, we did not have a lot of data on that element in our data, which makes sense intuitively. The other thing is possible is that there's something wrong with your data set. So this is if this doesn't make intuitive sense, then you should probably go back and make sure that all your data looks okay. If predictions are off to an unrealistic extent. All right. The next thing I have plotted here are confidence intervals. So the important thing is that while it is important to get accurate predictions, it is also important to know how confident are you in your predictions. And for that, it is important to basically do some kind of uncertainty quantification of your model itself. So as I know off the top of my head, there are two ways of doing this, which are most common. There's someone called use statistics, and then there's the jackknife bootstrapping method, which is what I use here. So what you basically do is you take your training data and you randomly leave out subsets of that data, and you train your model on that data, and you keep doing this iteratively until you have a large data set, a large number of models, and then you take the average of the results of those, and then you plot them. So what you end up seeing here are the error bars for these predictions. So the first thing to note is that we have a lot of these bars which are crossing this calculated equals the predicted band gap line, which is good. That is important. That shows that most of our predictions are very reliable. The second thing is that you see that the materials that have a very large error bar, they are further away from this line. So basically, it tells you that that the uncertainty is higher for the predictions that are actually further from reality as well. So that is good. That is a good, just back of the envelope check to make sure that everything looks good. The next thing is that now that we have both these models, we are going to use these models to predict the new oxides, perovskites with wide bandgap. So if you just remember what I went through in my slides, we had around 1 million materials. So those million materials, when we passed them through the stability and the formability models, we ended up with around this number, which will appear here shortly because I just ran this thing. So we ended up with around 500,000 materials, which are predicted to be formable and stable. And these are the materials that I would ideally like to run through my insulator classification and bandgap prediction models. So now the problem is that this is a very large data set. And if I try to use it in this notebook, the kernel restarts. So for the purposes of demonstration, I'm only going to use about 1/5 of these, about only the first 100,000. So I take a condensed candidate data. I only take the first 100,000 of these data, and then I prepare them for my next models. Okay. So then I just take a look at what this data looks like now, and it's pretty similar to what was there earlier, right? Okay. So the next thing to do is that, again, because I have very large data sets here, it's not very fast. So to speed things up, I clear some memory by deleting some data that I no longer use, and that will just make the whole thing much faster. And then I use run these 100,000 candidates through my insulator classification model. And I see that it tells me that, okay, I'm putting in 100,000 materials, and out of those, around approximately 3,000 materials are predicted to be insulators. Okay. Yeah. So out of the this is my original number of candidates, which are 6. So if I was actually using the whole data that I had, I would have 16,000, around 17,000 materials predicted to be insulators. But here I only have 3,000 because I'm only looking at a subset of the data. Okay. So the next thing to do is that for these 3,000 materials, I would like to predict the bandgap. Okay, so I have done that, and I will plot the predicted bandgaps. And here I see that of all these 3,000 materials, these are what the bandgaps looks like. Then again, they're also only predicted above 0.5 eV because that's how I've trained my model, and it goes up to 0.4 electron volt bandgaps. And things seem to be really concentrated around the 1.5 EV bandgap. This is a little skewed now because, as you saw, I'm only using the first 100,000 data points, and I don't really have all the data here. So, but when in my actual work, I kind of have a more uniform spread. Okay, the last thing we're going to look at is partial dependence plots, which are basically once you have trained your data, it is good to see what is exactly the. Actually, I'll just go ahead and do that because it takes a long time to run, so that while I'm talking, that it can populate. All right. So it's good to know that what is the dependence of your features? How does, when I change a feature, how does my bandgap change, right? So that at the end, I can have some idea of that, oh, if I want a bandgap that is in this range, I should be looking, my features should be in this particular range so that I can get the bandgap that I want, and so that I can choose the material that I want. So these partial dependence plots can basically be, they're basically one-dimensional or even two-dimensional plots. That basically tell you that what is the relationship between a featured pair and your predicted target property. And so we're going to have to wait a minute for that to load. And while I can do that, maybe I can take a look at the questions.
Yeah, Anjana, maybe I can quickly ask you one of the unanswered questions. How do you compute the confidence interval to show uncertainty of prediction?
You have so the short answer is that you use, I used uncertainty quantification package that scikit-learn supplies. But other than that, basically what you are doing, I thought I mentioned this, but anyway. So what you do is that, so I have, let's say 1,500 data points, right? Which I'm using to train my data. And let's say out of those, what scikit-learn automates for you is basically this. So it, out of those 1,500, let's say it just takes, it leaves out 20, and then it trains your model. Then it leaves out another 20 and trains your model. And it keeps doing this over and over again until it has when you specify the number of computations it wants to do. So for example, I will say that calculate the model 1,000 times by leaving out a random number of data. And once it does that, so at the end it has 1,000 predictions, right? So what it does is that for each of those points, it's averaging those predictions, and then you have basically a lower bound for a prediction and an upper bound for a prediction, which is what gives you the uncertainty. Does that answer the question?
Yeah, I think so. Great. If you want to answer another one quickly, did you use any GPUs in training?
We did not use GPUs. So we just used for the training, my laptop, MacBook, or even the desktop was more than sufficient. The training itself, I think the most, let's say, computationally intensive part was basically loading all the data more than anything, just carrying around data of around 5 and 5.2 million compounds, which is why we had to look at, ways to condense our data and look at, technically I was able to run my model for not more than, it doesn't really take more than a minute for at any stage, using just regular desktops and laptops. So no, we did not use GPUs.
Okay, awesome. Yeah, why don't you continue? Thanks. Yeah.
Okay, so then these partial dependence plots, or PDPs, that I was talking about, this is what they will look like, right? So you have, so I have listed here the top 5 features for my regression model. So then I have the electronegativity, sum of electronegativity on the A side, sum of electronegativity on the B side, average sums there. So then I have these two plotted here, and so you basically see here that yellow indicates larger band gaps, and then purple is obviously your lowest band gap. So what this basically tells you is that you basically need a the average electronegativity on the X side, it should be around 1, and on the B side it should be around the 1.6 mark to get your maximum band gap. So now it is important to note that this is basically just a projection, or it's interpolating. So technically, even if I give you these ranges, it's highly possible that you can't actually find a compound which is in that range. So you have to keep that in mind, that this basically tells you that looking at these features, this is what you should be looking at. So then I also look at, let's say, the third one, and the first one, let's say. So here it tells you that if you want the highest band gap is again, so this is good. It's because it's consistent. You see that XA is up till 1, and again for this combination also, you need to keep your electronegativity on the A side up to 1. Anything more than that is going to reduce your band gap. And again, you want to keep your pseudopotential radius here is a pseudopotential radius to below 1.75 if you want to maximize it, or even if you or else if you specifically want something which has a band gap in the range of 1.7, then this is where you should be looking at, looking at a average electronegativity of in this area and Z radius of this on the A side in this area. Similarly, this is the third, I just plotted it for the first 3 features, so that will give you 3 combinations. And we see with the XP side, it tells you that up to around 1.55 and around 1.75 again, which is good because this is corresponding to this, that this is where you will get, in this region, you will get your highest band gaps or lowest band gaps as you want. You can look where you want. So I hope that gives you some insight into how we did this work and how it can help you in your own work. And with this, I will go back to that marks the end of our tutorial. So we'll go back to my slides. So this is where we left off, and we did all this. And so now we are basically at this stage that we built all our models. We made sure that they're accurate enough to satisfy us, and then we applied them to approximately 1 million compounds. Applying our stability, thermodynamic stability and formability models reduced our space to about 500,000, around this number. And then when we further applied our insulator model, we got around 14,000 materials. Out of this, 14,000 is very small compared to 5.2 million what we started with. But at the end, it's still a very large number to actually do anything with. So here, this distribution plot shows you the predicted, these 14,000 materials, and there's the probability of them being insulators that is predicted by the model. So anything above 1 point, like I said, anything above 0.5 is predicted to be an insulator. So what we did is that we tightened this threshold to make it something to make it less than. We said that anything that is likely to be a insulator with a probability greater than 90%, I will pick out those elements. And I ended up with 304 of those, which so I basically, this is just magnifying this in the 0.9 to 1 range. So then I ended up with 304 elements, which I selected. And those are going to be the predicted band gaps of these 304 is shown here. So this is also good because these are all 304 elements, which are highly likely to be insulators with predicted band gaps in the range of 0.5 to 4 electron volts. So the next thing is that with these 304 electrons, this is so I just have here a Venn diagram, which basically shows the relationships of all the data that I've considered in my work. And I'm in the interest of time, I'll just move on. But it's basically, this just shows how the data sets are linked, right? We also computationally confirmed these results. Out of those 304 candidates, we picked 150 randomly, and we calculated their calculations. The good thing is that all of them have a wide band gap, so that proves that our insulator classification model was accurate. And the band gaps are all predicted with an average mean absolute error of 0.5 and 5 electron volt, which again, we are very happy with. So some more So before I take any questions, I would just like to do some, just summarize quickly what I think you should do when you're looking at using machine learning in material science. Use it only if necessary. Do not use it because it's a thing to do, and if you don't need it, you ensure that the code is reproducible with no ad hoc measures, and that all your data sources are annotated if applicable. If possible, have data and codes and scripts made publicly available in repository. And most importantly, if people contact you about your work, please answer those, because I have had this happen so many times to me that I don't understand something and I email people and I don't get responses, and that is really upsetting. So with that, I'll take any questions that are there, or I'll continue answering the ones that are in the chat if necessary.
Yes. All right. Perfect timing. Thank you very much, Anjana, for a fantastic tutorial. That was really great. Very, very, detailed, very thorough, and, great timing, as I said. So Ghanshyam has done such a great job of answering most of the questions already that, a lot of the questions have been answered. But I think what I can do is let me ask some of the questions so you can verbally answer, some of the ones that I see are unanswered. First of all, I answered a couple of them, but it may be, better if you answer them. One, there was a question on how do you choose DFT functional. So if you want to give your thoughts on that.
So that's so for us, we ended up with the PBE-GGA functional simply because we wanted to do a lot of calculations. We did 5,000 calculations. We needed something that's reliable, mostly reliable, something which is efficient and fast. And that is why, I can probably go back. So we went with the fast method. That is how we chose our DFT functional. But if you see this slide of mine, so our next step, which I do not really talk about today because there was not enough time to go into it, is that we know that the PBE-GGA functional is not completely reliable in terms. I mean, it doesn't estimate very correctly the band gap of the material. So we have another model in there which actually Ghanshyam has built. I have nothing to do with that, but he's built basically something which, given the PBE band gap, predicts the HSE band gap for the material. So it predicts a higher fidelity band gap. So it's a matter of basically when you're choosing your DFT functional, it's a matter of choosing the best functional that you can use for your task. For us, we needed something that was going to be fast to calculate, something which is sufficiently gives us a good estimate. So we went with PBE-GGA, but of course you can go with whatever depending on how many calculations you want to do, how much time you have, how much computational resources you have. Yeah.
Awesome. Yeah. Okay. There's a question from Amitav Banerjee. Why do we need a wide bandgap material for scintillation, especially if we consider having the cross scintillation mechanism? As we know, the cross scintillation enables a very fast, even sub-nanosecond scintillation response. Okay.
Now, first of all, Amitava is my lab mate, so he knows more than this than he's letting on. Secondly, Amitava, I did not talk about scintillators at all in this talk. So, okay. What he's getting at is basically the fact that I focus this talk on perovskite discovery, but basically the larger goal is to find new scintillator materials with wide band gaps. We are looking at oxide perovskites to find these materials. That is a good question. Why do we need a wide bandgap material for scintillator? So it's not necessarily that you need a wide bandgap material for scintillation, but you at least need something for which it has a band gap, let's say. So there is much more to the problem other than having a wide band gap. You need to know whether the activator states, whether they're in the correct levels or not. But as a base answer, you probably need to know whether it has a wide band gap at all. And when I say wide band gap, my wide band gap criteria is also pretty narrow, right? It's just 0.5 electron volt. So ideally, you're just making sure, which is basically inside the DFT error level. I mean, if it's highly likely that if DFT predicts something to have a zero band gap, it will probably be between 0 to 0.5 electron volts. So what you're my model is basically trying to screen out those that have a band gap, and we are introducing an arbitrary 0.5 electron volt in there to just filter out the ones that don't have a band gap. So maybe that is a little misleading, that we don't really need a wide band gap material, but we just need a band gap material which has a band gap. And that is why we approach the problem this way.
Okay, there's another question on, can this work backtrack the features of any target insulator if I want to know what are the features of one of the classified insulators? So I'm not sure, but maybe they're talking about the feature importances or finding out which are the important features.
Yeah, so that's what you should, I mean, of course, we can do that. That is what I was going into, the spatial dependence plots that would basically help that. So once you look at, let's say you have 10 features, and then you look at, basically you would be looking at those partial dependence plots for all those 10 features, and you would be trying to come up with ranges for all your features for a particular insulator. So yes, you can do that, definitely. Because the thing is that once, I mean, when you say that you want to know what are the features of one of the classified insulators, the feature is part of your data set. So you can definitely find access to that very easily, right? Because you are using it to train, you're also using it to predict. So maybe it was not clear, but all the features that are making up your model, your prediction data set also has to have those features. Otherwise, you cannot predict.
Yeah, great. Yeah. Okay, let's do one final question. Why do you consider only cubic structures, and within the cubic family have specific symmetry?
Yeah, so I think, yeah, you probably missed it. I did answer that question right in the beginning. So Amitabh, the thing is that we are doing high throughput calculations, and for every to keep the problem small, we went with cubic crystal structures only. The idea is that once we narrow it down to things, and we also have energy above hull limit of 50 electron volt, which basically makes 50 milli electron volt, which makes sure that we are not discounting those materials which might be stable in lower symmetry phases as well. So our idea is that, and I can if you look at our paper, we have described this in great detail. But the whole thing was that because we did 5,000 calculations, and if we were going to look at all the cubic structures possible, that would barely be it would be like 20,000, 25,000 calculations, and we did not want to do that. To keep it tractable, we kept stuck to cubic perovskites. The idea being that once we have identified chemical systems that are interesting, we can go in and look at all the crystal structures for that cubic phase. For the cubic system. Yeah.
Okay, fantastic. All right. I think we have answered almost all the questions. If we see any remaining questions, I will email it to you guys so you guys can answer. So I think we can just about bring this tutorial to a close. I want to thank Anjana Talapatra and Ghansham Pilania once again very much for this amazing workshop. So the tool will be available on NanoHub for everyone, and please check out these guys' paper on chemistry of materials and the follow-up papers. So this is a very special workshop for me. Ghansham is a long-time mentor to me. We go a long way back. So, regular NanoHub attendees would recognize me, but I never introduce myself. I am Arun Mannori Kanakitori. I'm an assistant at Purdue. Thank you once again, Anjana. Thank you very much. And thank you, Ghansham, for answering these questions. I think we can bring the tutorial to a close now. Thank you very much.